So we are pleased to have Dennis Gaitsgory from Harvard. He's actually in Boston right now. And he will speak about a chiral ring to rule them all.
So we begin? Yes, it's the beginning, the start? Yeah, all right. Hello, everybody. So, by the way, there is Sam here also. Sam Raskin. All right. It's a great honor for me to give this talk. Okay, so let's begin with the thing. It's about quantum geometric Langlands. So we work with, I'll basically read the slides. So that's what I'll do, and then I'll happily kind of insert comments. So working on algebraic closed field of characteristic 0, we have a smooth and complete curve X and a pair of reductive groups, group G and its Langlands dual G check. And so we consider the moduli space of G bundles, denoted bun G on the curve, and the same thing, but for the Langlands dual group bun G check. Now, so the main object we're interested in is so the category of D modules, but its derived version, well, denoted D mod and bun G. So now, the quantum case means that it's not ordinary D modules, but it's twisted version. For this, we pick a level, kappa. It's a symmetric G-invariant form on the Lie algebra. And so consider the corresponding twisted category. I don't have time to explain what this means. So, okay, let me assume that this is known. You twist by means of the corresponding power of the determinant line bundle on the moduli stack. All right, so for this talk, for simplicity, we will assume that the level is non-degenerate and irrational. So what this means is this. So we restrict our form to the Cartan, and we apply the critical shift so that if you want the form of the Cartan to be 0, the form in the original Lie algebra must be the critical minus half the killing form. And so we want that restriction of the Cartan to be non-degenerate bilinear form. And furthermore, we require that it be irrational, which means that on every simple factor, what the restriction of the Cartan is the irrational factor of the irrational multiple of the killing form. So now, the Cartan of the Langlands dual group is just a linear dual of the Cartan of your group, and so if you have a non-degenerate form, you can take its inverse, and in this way, and then transfer it back to the Langlands dual group, and so that this way you create for a level kappa on your group an opposite level kappa check on the Langlands dual group. So, and again, I emphasize that the critical pairing on the group is the level 0 for the Cartan. So the conjectural quantum global Langlands conjecture says that there is an equivalence of derived categories. One is kappa twisted D modules on bun G, and the other is, the twisted D modules on bun G check for the corresponding level, and also notice there is a negative sign there. Now, but the conjecture said it's not just an abstract equivalence of categories, it's uniquely characterized by a certain property. It's called Whittaker-Kazhdan-Lucy compatibility, which I'll explain. Now, I can't really explain it in full generality. I can, but it will involve too much notation. I'll explain the most basic case. It's called the vacuum case, and I'll leave it to your imagination how to proceed with the general case. So what we do is this. On the one hand, for the group G, we can consider the following functor. First of all, you have the forgetful functor from twisted D modules to just quasi-coherent sheaves. And then you apply the functor of global sections. And in this way, you obtain the functor from this category of twisted D modules to the category of, vector spaces. And again, all functors are derived. So when I write vect, I mean chain complexes of vector spaces. So, and we denote this functor by gamma sub g. Now, for the same, well, that's one functor that you can create on your, out of your category. Now I'll create another functor of very different nature. So what we do, we consider the maximal unipotent subgroup of our G, which is the unipotent radical of the Borel. We consider bun n, which is the moduli stack of principal n bundles on the curve, but not quite that. We'll have to twist it a little bit. And it'll be not bun n, but I'll denote bun n with omega, and omega stands for the canonical bundle on the curve. So I'll explain what this twisting is for the case of SL2, and in general you do the same with each simple root. So what you do is this. So bun n for SL2 classifies short exact sequences of vector bundles, so just extensions of the structure sheaf by the structure sheaf. And now this twisted guy classifies extensions, but not of the structure sheaf, not of O by O, but of the. So what you do, you take omega, it's the canonical bundle on the curve, you pick a square root spin structure, and you consider extensions of its inverse by itself. So that's the twist you apply. You just replace the structure sheaf by some other line bundle. So now, the claim is that this, so why do we apply this twist? Namely, the claim is that this twisted moduli stack admits a canonical map to the affine line. So the affine line, so the map is obtained by, if you look back at the previous slide, you have the extension of one line bundled by another. These extensions are classified by H1, and by stereodiality, this H1 is canonically just the affine line. You take the class of the extension. And so that's the map that I denote chi. And so finally, you're able to define this new functor from the category of twisted D modules to, well, vect. It's called the functor of Whittaker coefficient. And the functor is obtained as follows. So when you want to apply it to an object, you take your object on bun G, on the one hand, you restrict it to this bun n omega, this twisted form of bun n, and then you tensor it up by the pullback of the exponential D module on the affine line. So you have this map chi that goes from bun n to A1, and you pull back the exponential D module. You tensor them together, and then you take the de Rham cohomology of the result. So this is the functor. So and now we can state the so the Whittaker-Kazhdan-Lucy compatibility. It says the following, that so this equivalence of categories must make the following two diagrams commute. One diagram is you take the first functor gamma for bun G, and the other functor, the functor of coefficient for bun G check. And it should make the corresponding diagram commute. And then there is another diagram which is symmetric. Just swap the roles of G and G check. So you apply the coefficient functor on bun G and this functor gamma on bun G check. So you want both these diagrams to commute. Okay, so this is the conjecture. It was proposed in more or less the same form by Fagin, Frankel, and Stoyanovsky some 15 years ago. And along with this conjecture, what they basically propose how they want the solution to be. So I'm not yet proving the conjecture, but I'll provide kind of a construction which is exactly takes the form that they wanted. All right, so what I mean is the following. So let's start with two algebraic stacks, x and y, and under reasonable assumptions, functors from d modules on x to d modules on y, not just all functors, continuous functors, functors that commute with arbitrary direct sums, are in bijection with kernels. These are just d modules on the product. Now, the same story goes through when instead of d modules, you have twisted d modules. So these functors are in bijection with twisted d modules on the kernel, but also note that there is a sign change. You start with kappa twisted d modules, but the kernel is minus kappa twisted d module. So therefore, to look functor is the same as to look for the kernel. I call it Q, which is the twisted d module on the product. And now the properties that the functor needs to satisfy can be tautologically written as properties of the corresponding kernel. So I won't write them explicitly, But so what we want a kernel satisfying this Whittaker-Kazhdan-Lusztig compatibility. So that it is this kernel that we want to construct. So what I'll do now, we'll explore a certain universal way of constructing D modules on bun G. But secretly, our G is G times G check. So we want to construct the kernel, which is the D module.
We lost you, Dennis. Dennis, we lost you.
So yeah, that's the slide where I lost you.
Okay, that's perfect. We can probably
Yeah.
and then put you there.
Gave people a chance to breathe. All right. So resume, yeah? Yeah. So looking at the category of Kac-Moody modules, and this little subscript x indicates that the Kac-Moody algebra is constructed of the ring of formal powers series, and this ring of formal power series is the local ring at a given point x on the curve. All right, so now, so on the one hand, you can consider all Kac-Moody modules, but we'll be mostly interested in a different version. I called it the Kazhdan-Lusztig category, well, at level kappa, again, at the point x, where we consider not just Kac-Moody representations, but those that are integrable with respect to, well, G of t. So there's a group of G with values in the local ring. So Kazhdan-Lusztig, because this is the category that was studied by Kazhdan-Lusztig in their papers on the connection with the quantum group. So now there is a canonically defined localization functor from this Kazhdan-Lusztig category. Well, the category depends on the point and the functor depends on the point, to D modules on bun G. And this, well, again, I don't have time to describe the functor. It's defined with the procedure of taking conformal blocks against a variable background G bundle. So it's a well-known construction. So now one can generalize it. So instead of having one point on the curve, one can take a finite collection of points, and the functor will now go from the tensor product of these Kazhdan-Lusztig categories at these points x1 through xn to the same target category twisted D modulus on bun G. So one can do it, well, even more, one can think of abstractly of Kazhdan-Lusztig as a factorization category. All this means is we have this ability for every finite set to consider the category that now lives over, well, x to the power of this finite set. So we're allowing these points to move and collide, and we still have the localization functor. And ultimately, we can take the direct limit over the category of finite sets and surjective maps, and we obtain the space that's, well, Bennett and Rintel called the round space. It's the space of all finite non-empty subcollections of points of the curve. We have the corresponding version of the Kazhdan-Lusztig category and the localization functor from it. So that's kind of the version of the localization functor that we'll be using. So what we want to do now, I want to explore the notion of a chiral algebra endowed with Kac-Moody symmetry with respect to G at level kappa. So one way, kind of naive way to do it is this. We denote by, well, we start with a Kac-Moody vertex algebra at level kappa. And so to have a chiral algebra with Kac-Moody symmetry at level kappa means by definition this. So we fix a map from the Kac-Moody chiral algebra to our chiral algebra of interest, but we impose the condition that when we view this A as a Kac-Moody module, that it belonged to the Kazhdan-Lusztig category. In other words, that the adjoint action of the Taylor series with values in the Lie algebra integrates to an action of the group Taylor series with values in G. However, so the notion of factorization category allows to, well, make more efficient definition, and it is as follows. We consider the factorization category, so this our Kazan-Luste category, and if you have a factorization category, it makes sense to talk about factorization algebras in it. So, and by definition, a chiral algebra with Kac-Moody symmetry at level kappa is a factorization algebra in this category. So in particular, if we have such A, we can consider the corresponding object over the round space, and we can now apply to it our localization functor, and in this way, we obtain a functor that, well, an assignment, if you start with chiral algebra with Kac-Moody symmetry at level kappa, you obtain a D-module, an object of the category of twisted D-modules on band G. So that's the universal procedure, and that's how we want to get our kernel. So returning to our object that we want to construct, this Q on the product, so what we want to do, we want to find a chiral algebra, I call it M for master, with Kac-Moody symmetry, but with respect to the product group, G times G check, such that when I apply the procedure that we've just described of localization on the moduli space, we obtain our kernel. So this is, by the way, the form in which Fagin, Frankel, and Stoyanovsky wanted to get their kernel. So, and indeed, we will be able to construct this chiral algebra, but it will only make one of the diagrams commute. So if, and the conjecture is that it in fact makes both diagrams commute. So if the second diagram commutes as well, then the constructed functor, you can prove that it's automatically equivalent. That it will prove this, the quantum global Langlands conjecture. But unfortunately, we can't do it at the moment yet. So another feature that I want to point out of the master chiral algebra is that its construction is asymmetric in G and G check. However, the resulting object, you can prove that it is symmetric. But so we conjecture that the chiral algebra itself is symmetric. So the construction, well, in the construction, the roles of G and G check are different, but the outcome must be such that, like, well, it is symmetric in G and G check. And let's emphasize that this last conjecture is local in nature. So, the previous conjecture about the kind of the two diagrams is global. So the global conjecture would apply quantum global geometric Langlands, but not the local one. All right, so we'll now proceed with the construction of this master chiral algebra, but before we do this, let's address a much more basic problem. So namely, let's consider just our band G, and let's consider the identity functor from the category of twisted D modules to itself. And we can ask, can we define this identity functor also by means of a chiral algebra? So what we want now is a chiral algebra with a Kac-Moody symmetry with respect to G times G. There's no Langlands duality involved at level negative kappa kappa. So such that the object of the category of twisted D modules on the product is obtained via this localization procedure described above. Now, this chiral algebra indeed exists, and it's the chiral algebra of differential operators on the group at the given level, minus kappa kappa. So this theory of chiral algebras differential operators was developed by Gorbunov, Malikov, Sheckman, and Weintraub, and from a slightly different perspective by Belenson and Rinfeld. So you can indeed construct this guy, and I can tell you how it looks like from the point of view of representation theory. So first, the vacuum representation, what it must be a bimodule for the Kac-Moody algebra. So one action is at level minus kappa, and the other is at kappa. So when used just as a module from the left action, it looks like this induced representation as written. And, well, in fact, it has a bimodule, structure where, well, the action on the left is the full Kac-Moody, and on the right you have just Taylor series acting. But the claim is that this guy has a unique structure, you can extend the action of Taylor series on the right to the action of the full Kac-Moody. So that's how the vacuum representation looks like. All right. So this is the chiral algebra that defines the identity functor. But now, so we want to use it to construct our master chiral algebra. But in fact, if you look at the commutational diagrams, this construction is algorithmic. You kind of follow, well, you have no choice in kind of passing from one to another. So namely, what we do is this. You consider this chiral algebra of differential operators as a factorization algebra object in the tensor product factorization category. Take Kac-Moody Kazhdan-Luste category at level negative kappa, tensor Kazhdan-Luste category at level kappa. And so the master chiral algebra is obtained from our chiral algebra of differential operators by applying a certain functor between factorization categories. This functor will go from the tensor product of the Kazhdan-Luste category for G at level negative kappa times Kazhdan-Luste category for G at level kappa to, well, the same thing along the first factor times the Langlands dual thing along the second factor. So, in other words, the functor that we want to construct will be the functor between tensor product categories. It will be identity along the first factor and a certain canonically defined functor from the Kazhdan-Luste category for G at level kappa to the Kazhdan-Luste category for G check at level negative kappa check. So this is what we'll presently describe. So this functor that we want to construct will be a composition that looks as follows. We'll first go from Kazhdan-Luste category for G at level kappa to a certain category that I'll presently describe called the Whittaker category for the Langlands dual group on the affine Grassmannian. And this is the step that involves Langlands duality. And then the second step will be, well, it will not involve Langlands duality, it will just occur for the Langlands dual group. It will go from the Whittaker category to the Kazhdan-Luste category. So that's what we'll do now. All right. So, as I said, this Whittaker is the twisted Whittaker category on the affine Grassmannian. Okay, so now what is it? For our group, we consider the affine Grassmannian, and it's also like the Banjit for level kappa, you can consider the category of kappa twisted D modules on it. And so this category is acted on by the loops into our maximally nilpotent subgroup. And the Whittaker category is obtained by taking co-invariance of this action against a character, well, the same cousin of the character chi that we mentioned before. It's a non-degenerate character of the loop groups into N of conductor 0. Well, again, it's some certain well-known canonical procedure of taking the Whittaker category. So now the first step is that there is a canonical equivalence of factorization categories as written. So Kazhdan-Luste category for G at level kappa and the Whittaker category for the Langlands dual group on the affine Grassmannian. So this conjecture has been made some 5 or 6 years ago, and it's a work in progress by Jacob Lurie and myself. So we essentially know how to prove it, but there's a lot of foundational material that has to be written down, such as what factorization categories are. Now, this conjecture is really the point of departure of both local and global geometric Langlands. So, like, initially people thought that Langlands correspondence starts with geometric Satake, but in fact, this is a more basic equivalence from which you can obtain the geometric Satake. All right, so we've performed the first step. So we went from the Kazhdan-Luste category for G to the Whittaker category for the Langlands dual group. And now we have to perform one more step to go from the Whittaker category to the Kazhdan-Luste category, but this step involves no Langlands duality. So that's what we're going to do. It's this functor from the Whittaker category to the Kazhdan-Luste category. And we'll apply it for G check. So what we do is this. So, well, this may be the more technical part of my talk. we consider the loop group itself. It's equipped with a natural projection, I'll call it pi, to the affine Grassmannian. And we have the following commutative diagram. So you can pull back d modules from the affine Grassmannian to the loop group, and both categories can be projected to the corresponding categories of coinvariance with respect to these loops into n. So both categories admit this Whittaker quotient categories. So it's shown in this commutative diagram. So now, why did I mention the loop group? Is because in the loop group you can take global sections. So there is a functor of global sections from d modules, twisted d modules in the loop group that goes to the tensor product of the full category of Kac-Moody representations at level G times the same category but at the reflected level. Now we have another commutative diagram. So as I said, you can pull back d modules from the affine Grassmannian to the loop group, and on the loop group you can take this functor of sections. Now when you compose it with the pullback with the affine Grassmannian, what you'll end up having is a functor from the affine Grassmannian, but to the product of all Kac-Moody representations tensor the Kazhdan-Luster categories, because, well, the condition of coming from the affine Grassmannian is exactly this equivariance with respect to Taylor series into G. Okay, now we are nearly there. Now you recall that there is a functor of BRST reduction with respect to loops into the unipotent group that goes from all Kac-Moody representations to just vector spaces. So it's BRST reduction against the same character, the same non-degenerate character. And finally, so we concoct the following following commutative diagram with 3 rows. And so you have this composite functor. You start with d modules in the affine Grassmannian. You take sections over the loop group, and then so you obtain a module of the object of the tensor product. So you have Kac-Moody at level kappa acting on the left, and well, the structure of object of the Kazhdan-Luster representation, Kazhdan-Luster category on the right, and then you kill the Kac-Moody action on the left by taking this BRST reduction, and you end up with just having functor from d modules on the affine Grassmannian to the Kazhdan-Luster category. Now, the main observation is that this functor, in fact, factors through the Whittaker quotient. This factor, so we call it the Whittaker quotient, is coinvariance with respect to the action of some group. And the claim is this composed functor, I mean, going the composed left arrow in this diagram, exactly satisfies the condition of being invariant. And so in this way, you obtain a functor from the Whittaker category on the Grassmannian to the Kazhdan-Luster category. All right, so we've gotten this functor, and then you compose with what we said before. You obtain a functor between Kazhdan-Luster category, tensor Kazhdan-Luster category for this group G to the corresponding category for the group G times the Langlands dual. You apply it to chiral differential operators, and you get the master chiral algebra. So, well, to conclude, let me just, well, describe what the vacuum module for this looks like. After all, it's a vertex algebra. You can take the vacuum module, it's a representation. It's a representation of, the Kac-Moody algebra for G and the Kac-Moody algebra for G check. And let's say what it looks like. So now the claim is that if you follow through the construction, so yeah.
We just lost you a couple of minutes ago, Dennis.
Okay.
So let me show you the slide, and it's probably better to start at the beginning of there.
Yeah.
Thanks.
So, oh, that's the same slide.
Yeah. Just
Yeah.
a second.
Yeah. So I'm saying that by construction, our master chiral algebra admits homomorphism from the tensor product vertex algebra, namely the Kac-Moody vertex algebra for G and the Kac-Moody vertex algebra for G check. But now, if you follow through the construction, in fact, this homomorphism extends to a richer structure. So namely, you can tensor the Kac-Moody vertex algebra for G, tensor one from G check, but also in the middle you have the W algebra for G check at level kappa check. So now also notice that, well, we conjecture that the master chiral algebra is symmetric for that reason. So the chiral algebra from which it receives the homomorphism had better be also symmetric. And indeed, this is ensured by the Fagan-Frankel isomorphism, namely the W algebra at level for G check at level kappa check is isomorphic to the W algebra for G at level kappa. So our master chiral algebra is supposed to receive the homomorphism from this triple tensor product. In particular, its vacuum representation is a module for this triple tensor product. And let me describe explicitly what this module looks like. So it looks as follows. Again, this description is valid only at the irrational level. So as a module, it's a direct sum, it's a double direct sum over lambdas, which are dominant weights for G, lambda checks, which are dominant weights for G check, of the following terms. So terms will be a triple tensor product. On the first factor, we'll have Kac-Moody for G acting. On the second factor, we'll have the W algebra acting. And the third factor, we'll have the Kac-Moody for G check acting. So the first factor is the while module at level kappa with highest weight lambda. And the third factor, I forgot the lambda check there, it's the same thing, but for the dual Langlands dual Lie algebra. So now, what's the middle term? So what's the star? Star is, if lambda is dominant weight, lambda star is not a dominant weight, it's minus W naught of lambda. W naught is the longest element of the while group. So I have to tell you what this module for the W algebra looks like. Well, it's the following module. It's obtained from the Weil module for Kac-Moody by BRST reduction. So this bold-face W has two indices. It has mu check and mu. So one is dominant weight, another dominant co-weight. You start with sorry, it's a typo here. You start with the Weil module of weight mu, and then you apply to BRST reduction against the character whose conductor is mu check. And in this way, you produce a module for the W algebra. And that's the guy in the middle. So, and again, you take the direct sum of these over lambda and lambda check. And that's how the vacuum module for this master chiral algebra looks like. And I'm afraid that's it. Unfortunately, I couldn't pace myself well enough, so I'm 20 minutes early.
Any questions for Dennis? So Dennis, the question was, what is conductor? What does conductor mean?
Conductor is this. So it had a character on. So conductor is this. So suppose I have a character on loop group into N. Conductor will be a certain co-weight, and it's measured as follows. What's co-weight for every simple root? I have to assign an integer. So if you have a character of loops into N, first of all, because it's a character, factors through the quotient of N modulo the commutant. Now the quotient of N modulo the commutant is the product of copies of the additive group for one simple root, each for one simple root. So, and then you see what your character does on each copy. Now you have loops into the additive group and have a character of this, and you measure what's the highest power of T on which the character doesn't vanish. And your character vanishes on T to the N times Taylor loops, and you take the minimal such N, that integer is the value of the conductor on the corresponding simple root. That's how you measure the conductor. Yeah?
Could you repeat the last sentence, please?
Yes. Okay, so again, the character is supposed to assign an integer to each simple root. So by quotienting out, hello, can you hear me?
Yes. Yes, we can.
Yeah, it's okay?
Yes.
Yeah, so again, so I quotient out by the unipotent, by the commutant. So I've got a bunch of copies of the additive group, each for one simple root. So let me tell you what happens for each copy. So there you have the algebra is just Laurent series in one variable, and you have a character of that. So if you wish, this character is pairing by seriality with one form with values in the Laurent series, and you measure the order of the pole of this form, and that's the conductor. So it's an integer.
Okay. So the question is, can you prove the symmetry of W with respect to mu and mu check?
I can't hear. I can't hear. Can you come closer to the microphone, into the computer?
Yeah. Can you prove the symmetry of W between mu and mu check?
No, not even that. So that's part of the conjecture. I'm sure somebody in the audience can prove this, but not me. It's widely believed to be true, but I don't think it's known.
Dennis, can you hear me?
No, come closer.
So, and let me ask you a question. It's Reimundo. I want to ask you a question, but it's a foundational question.
Yes, please.
So, you described the construction of the Gaitsgory category as a factorization category.
Yes.
And in Beilinson and Drinfield's stuff, there's a chiral version of this. So I wonder if you have some sort of compound tensor 2 category, such that a Lie object there is a chiral category, a counterpart to your factorizations categories.
No, we don't have anything like this. No. No, see, there is obstruction to it because, see, actually, I don't know. So I don't know. See, so far, what we know how to say the word Lie in what's called the stable context. So Lie algebras make sense in vector spaces, or something like this. We don't know how to make sense of Lie algebras in categories. So like factorization categories are what's called E2 categories, and those can live anywhere. Like Lie is something more specific to when you have additivity.
Other questions? Okay, let's thank the speaker again.